Time of flight mass spectrometry can be used to analyse large molecules such as the pentapeptide leucine enkephalin. They're calling that P. P is ionised by electrospray. So remembering that electrospray doesn't knock off an electron, it adds a proton, and its mass spectrum is shown in figure 2. Describe the process of electrospray. So it's wanting us to describe the process of adding this proton. So how is a proton added to our sample P? So first thing we'll need to do is our sample P, which is a large molecule, is going to need to be dissolved in a solvent. That solvent is usually a polar solvent, and it's a volatile solvent, so it can be easily removed. It's then injected through a needle into the mass spectrometer that is at a high voltage. So the needle is attached to a high voltage power supply, and that is going to help us to the next part, allow the sample to gain a proton from the solvent. And remembering a proton is H+. So if we were to write an equation for that, P, which would be a gas, is picking up a proton from the solvent to become pH+ gas. And as a result of that, when we want to find out the relative molecular mass, 556 is pH+. So if we want to find out P, we need to subtract 1 to get rid of the H. The H has a mass of 1, so we need to subtract 1. So our answer is going to actually be 555. And then now a different molecule Q is ionised by electron impact. This just means it's knocking off electrons, so it's just going to become Q+ in a time of flight mass spectrometer. The Q+ ion has a kinetic energy, so this is our Ke, of 2.09 times 10 to the minus 15. Time T is 1.23 times 10 to the minus 5 seconds, and the length of the flight tube D is 1.5 metres. Calculate the relative molecular mass, that's the MR, of Q. So the first thing that we're going to need to do for our sample is work out the velocity by doing the distance divided by the time. So 1.5 metres in 1.23 times 10 to the minus 5 seconds. So on your calculator, you want to put those numbers in. We're getting 1.21951 metres per second. Now, you don't need to keep that many significant figures, but I'm going to keep the number on my calculator. You could go to 3 significant figures, so 1.22 times 10 to the 5, or 1.22000. All those numbers would be acceptable. Now, if I rearrange Ke equals half mv squared, what we're going to see is if we times by 2, we're going to get 2 times Ke equals mv squared. We remember we're trying to find mr, so we're going to need to find the mass. So if we divide both sides by velocity squared, we're going to get mass is 2Ke over v squared. So we're going to go, the mass is 2 times the kinetic energy, 2.09 times 10 to the minus 15. And then we're going to divide it by our velocity squared, so our 1.21951 squared. At this point, I'm going to use the feature on my calculator that allows me to use the answer. So I'm going to use the fraction button, type in the top line, go to the bottom line and press answer so that I don't lose any of the sort of accuracy of my answer. But remembering that we have to use answer squared. And we're getting 2.81 times 10 to the minus 25. Now this is going to be in kilograms, because when we calculate kinetic energy, mass is in kilograms. And relative molecular mass is the mass of 1 mole in grams. So the next thing I'm going to do is turn it into grams. So 2.81 times 10 to the minus 22 grams. Then I'm going to find it for 1 mole. So I'm going to times by Avogadro's number, which they've given to us up at the top. So times 6.022 times 10 to the 23. And I'm getting 169.3 grams per mole. So my MR is 169 or 169.3. I don't need to keep all those significant figures. I'm just going to round to 169.